This video is for Math 116, and this is for section 3.3 in the textbook, which is about mathematical series, which is a series of numbers that are being added together. Okay? So because they're being added, in mathematics we use the capital Greek letter sigma to represent the sum. Okay? So let's see. The example that I give in the textbook here, this is on page 112. So if we have these numbers being added together, 1 plus 5 plus 9, 13, 17, 21. So to represent this, we want a general formula for these numbers that match to the term or the number of each term. Okay? Actually, I have this bad habit of using n in these situations, whereas it's generally accepted in mathematics to use something like I, J, or K. I think in the textbook I've used K in most situations. Okay, so you can see the relationship, the similarity between the series and the sequence, and I'll talk more about that as we work through this material. But this is the first term, second, third, fourth, fifth, and sixth. Okay, so the way we write this is, first off, we develop a general expression for each term based on the number of the term. Okay, just the same way that we did for sequences. And in this one, you can see there's a constant difference here of 4. So this would be 4k. If k is starting at 1, then we would need to subtract 3 each time. So the first one will be 4 minus 3 is 1, and then 8 minus 3 is 5, 12 minus 3 is 9, and so on. So 4k minus 3, and k starts at 1 and goes up to 6. So there's an expression that represents this series. Now I mentioned in the textbook there are other ways to go about doing this. Like if you identify the 1 as the 0th term with k equal to 0, and then k equals 1, 2, 3, 4, and 5, well then our 4k would have to get 1 added to it. If k is 0, then 0 plus 1 is 1. And then when k is 1, 4 and 1 is 5. So if we set it up like this, 4k plus 1, then we would need to run k from 0 to 5. So both this and this represent the same sum, and neither one is correct or incorrect. Okay? Sometimes when you have to combine these things together, you need their indexes to match up with each other, so that's why sometimes people play around with that index. That's the k is called an index. Okay, so there's the first example. And this is a finite series because it has an ending term, right? There's no dot, dot, dot at the end of this. All right, the second example I give on page 112 is an infinite series. And this one is a classic. This is k equals 1 to infinity, 1 over 2 to the k power, so that'll be a half, a fourth, an eighth, a 16th, and so on. Okay? And so, infinite series are kind of tricky to work with. They can do unexpected things sometimes. This series, it's kind of interesting. You can kind of arrive at an approximate value for this sum. This actually, if you add these all up, is approximately equal to 1. In fact, and in calculus you get into the definition of a limit, okay? Where a limit says that this is going to be indistinguishable from 1 at some point along the way here, okay? If it's not close enough for you, we can just add more terms in there. We can get as close to 1 as we want to without it actually ever being equal to 1, okay? So it is typically an approximation. But this infinity symbol really does make it equal to 1, right? Because if you could add on terms infinitely, then in theory it would be equal to 1. But again, our human beings' relationship to infinity is kind of tricky. Okay, so before I erase this, I want to talk about the connection between series and the sequences that we had talked about and why they're frequently studied together. Okay? So in trying to figure out what the sum of something might be, frequently mathematicians look at partial sums. So this is the sum of the first term. The second partial sum is the first 2. The third partial sum is the first 3, and so on. And you can see how this is getting closer and closer to 1, right? If we had, let's see here, well, s to the 4th is going to be 15 over 16. S5 is going to be 31 over 32, and so on. Okay? And so typically, now we've got a sequence of partial sums that we can try to find the limit for, or we can try to see where that sequence is headed towards. Okay? So that's the relationship between sequences and series. This first section on mathematical series is mostly just about the notation. All right? It's mostly about, I'll make a kind of a less sloppy capital Greek letter sigma. All right? It's using that sigma notation to represent a sum. So, in the problems on page 113, we start out just taking one of these summation notations. K here is running from 3 to 7, and our formula is 6k minus 3. So, what we want to do here, write out each series in expanded notation. That means write out all the terms of the sum. So we'll have 6 times 3 minus 3, and then 6 times 4 minus 3, 6 times 5 minus 3. And you don't have to write this all out. You can just write down what each one of these is equal to. But I'm writing it out just for the heck of it. Let's see here. And then 6 times 7, or actually, I'm writing it out to more clearly illustrate what's happening. All right, so let's see here. So this is going to be 18 minus 3 is 15, 24 minus 3 is 21, and then once you get the, and you can see this is an arithmetic relationship with the common difference of 6. Let's see, 27, 33, and 39. And there it is. That's the expanded notation. You can add those together if you want, but what I'm looking for in your answer is this expression, okay? Just the representation of each of these terms being added to each other. All right, let's see here. That's problem 2. Problem 4, you see we've got that negative 1 to the k plus 1 power in there. So that's going to make this an alternating series. An alternating series, this is a finite alternating series. The infinite alternating series are sometimes even more baffling than the regular infinite series. Let's see, k from 0 to 10, negative 1 to the n plus 1, k plus 1. See, told you I have a bad habit of using n there. There we go. And then times k minus 4. Well, that's a pretty simple formula. The only thing that's a little bit out of the ordinary about it is this negative 1 to the k plus 1, and that's just going to make it alternate. So if we plug the 0 in here, that's going to give us negative 1 to the first. Plug the 0 in here, negative 4. So that's our first term. Second term, we'll have a positive 1. 1 minus 4 is negative 3. Well, I called it the second one, but if this is the 0th term, then this is the first term, and so on. Let's see here. The next one, we'll have a negative 1. And let's see, let me write down the value of k here. 2 minus 4, negative 2. and then positive 1. 3 minus 4 is negative 1. Negative 1, 4 minus 4 is 0. Positive 1, 5 minus 4 is 1. Let's see here. So, where are we next? Negative 1 times 2, positive 1 times 3, negative 1 times 4, and then we got two more terms. Positive 1 times 5 and negative 1 times 6, right? Because when k is 10, 10 minus 4 will give us the 6. 10 plus 1 is 11, which is odd. That gives us a negative 1. And I'll go ahead and fill these in. And so those are the values of k. And then the value of this expression for that value of k is underneath it. And so what are we going to get here? We're going to get 4 minus 3 plus 2 minus 1 plus 0. You can call it minus 0 if you want. Plus 1 minus 2 plus 3 minus 4 plus 5 minus 6. And again, we don't need to calculate this. All I want to see is you translating this into the expanded notation. Okay? All right, let's see here. Problem 6, we got one more of these. And again, you can skip this part and jump right to just writing out the values. Because once you pick up on the pattern that's happening, it can be easier just to write them out rather than calculating. All right, so here k runs from 1 to 8. And our formula here is k over 3 to the k power. So that's going to be 1 over 3 to the first, 2 over 3 squared, 3 over 27, 4 over 81, 5 over 243, 6 over, what is that, 729, 7 over 2187. Let's see here. So this is going to be 3 to the 7th power, 2187. And then 8 over 6561. And again, we don't need to add these up. I just want to see it in expanded notation. All right, let's see here. Okay, so that's the first half. It is taking the sigma notation and writing it out as a sum in expanded notation. In the second half of the assignment, we've got things that are written out in expanded notation, and we want to rewrite them using the sigma notation. All right, these are all finite series. So, problem 8, 5, 10, 15, 20, 25, and 30. Okay, so this, you can see we've got a common difference of 5. And so if we just say 5k and start k at 1, then that should work. 5, 10, 15, and so on, up to k equals 6. Okay, so there's problem 8. Problem 10. Let's see here. 5, 8, 11, 14, and then we've got a dot, 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 and then it ends at 95. All righty? So again, you've got a common difference. These are both arithmetic. Here the common difference is 3. So let's see, if we start k at 1, then here we would need to add 2, right? 3 plus 2 will give us that 5. And then 6 plus 2 will give us the 8, and so on. Now the question is, how far does k going to go? Well, what I would do to figure that out, I would take the 95, subtract 2 from it, and then divide this by 3. And so that'll give us 31. You can do guess and check, works just as well. But now so that k equal to 31. There's our 93 plus 2 gives us 95. Okay, let's look at a couple more here. And like I said, this assignment is just about the notation. In the next section, we'll talk about more about the how to work with series, both infinite and finite series. Problem 12, 1, 8, 27, 64, and then we end at 1331. So this one is a little bit tricky to recognize what's happening here. But since I made the problem, I know what's happening here. These are perfect cubes, okay? Perfect cubes and perfect squares. I think I mentioned in one of those previous sections on sequences are good things to keep in mind if you're trying to find a formula for something, okay? So this one turns out to be perfect cubes. So this is 1 cubed, 2 cubed, 3 cubed, 4 cubed, and so on. So let's see, I'll start the k at 1. And then the question is, how high up does this go? I think that's 11 to the third. Let's see here, 11 to the third power, 1331. Yeah, so this goes up to 11. Now you might say, well, what if I wanted to start k at 0 here? How could I do that? If you're starting k at 0, you would then need to add 1 inside the parentheses, and this would go up to 10. So now there's your 1 cubed. When k is 1, that'll give you 2 cubed here. When k is 10, the last term here, that'll give you 11 cubed. And so either one of these is fine, okay? All right, I think we've got one more to look at. Problem 14. So this is an alternating series. Let's see here. 27 minus 9 plus 3 minus 1 plus a third minus a ninth. So here, if you think about this in terms of constant multipliers or constant ratios, the constant multiplier here is a third, and more specifically, it's negative a third, okay? So, let's see here. Now, we can include that negative in our formula. We can separate it out if we want to, or we can put it inside the parentheses with the 1/3. So, let's see here. So, we'll start off with the 27 as a coefficient, and then negative 1/3 to the k. It depends. So if I'm going to start k at 0, then this works just fine, right? K equals 0, this to the 0 power is 1, there's our 27. When k is 1, it'll be 27 times negative a third, which is negative 9, and so on, okay? And we can just count off here, 0, 1, 2, 3, 4, and this will go up to 5, okay? That's one way of going about it. If you wanted to start k at 1, then what would we do? Well, the easy way out is to have that negative 1/3 and just put the k minus 1 up there, and then it would go up to 6. So there's another valid representation for that series. And I think I'll just leave it at that, okay? We'll play around with this more in the next couple of sections in the textbook. And like I keep saying, this section is really just about the notation. It's just getting comfortable, getting familiar with this sigma notation, which, depending on which calculus course you take, it becomes very important in calculus. It's interesting, actually, series, infinite and finite series, are actually one of the very first things that Isaac Newton did when he was developing his methods of calculus. But for some reason, in the teaching of calculus, this is typically taught last. So we teach it in our Math 253 course. Most of the universities have a Math 253 where they talk extensively about infinite series. And it's really, really important material because so many equations just can't be solved by regular algebra. and they have to generate one of these formulas that's like, here's your answer. And it's like, well, what number is that? So that's where mathematicians come in to try to figure out what series will represent the answer, and then calculate what that answer actually is, and also what the error might be. Because if you're working with an infinite series, if you take a finite number of them, then there's always going to be an error in it. Anyway, if you have any questions on this, please let me know. And like I said, as we move on, we'll work with these a little bit more.